All right, guys. Welcome to video. We're going to be going over finding prime numbers. Um, in order to, well, this is actually something that's very common on Project Euler. A lot of their, a lot of their early examples ask you to find something to do with primes, right? So, determining the primality of a number is actually pretty key to some of the basic algorithms that they have. You can see just on the first 50, um, you know, they've got a few. This one is, I think, the most straightforward. So I thought I'd start out with that to give you an idea of how to find prime numbers. So the prompt here, if we list the first six prime numbers, 2, 3, 5, 7, 11, 13, we can see that the sixth prime is 13. We need to find the 10,000 first. So first thing that we're going to do is always um, find our function. Uh, so we are going to call this function. The target is going to be the number, the prime number that we're looking for. And we are going to return let's return um, we can we could do unshift and return the first member of the array. There are going to be reasons that I'll get into later on as to why we probably shouldn't do that. But you can. The basic ways that I'm going to show you. You can just, instead of using r dot push, you can just do unshift and return the first item of the array rather than the last. You could also just set it up so that you don't actually need to calculate, because that should be the same. So let's just go ahead and do that. That's going to be the most straightforward way. That way, no matter how we write it, it's going to be set up like that. There are going to be two iterations that we're going to have to do. One, we're going to be iterating through numbers to check if they're prime. And then two, we're going to be iterating through numbers to check if they can divide the number. So we're going to be checking the dividend, or we're iterating through the dividend and iterating through the divisor. So let's declare our dividend first. We're not going to start at 1 because I don't know of a way to check for primes where 1 doesn't get included in it unless you just carve out an explicit exception for 1. So it's easier just to start at 2. Because if you started at 1, you're going to have to say, if blank equals 1, then skip. We're going to be checking for primality of something. So the easiest way to do that is to say, is something prime? Yes. Then, push it into this array that we have. Easiest way to, set something to a yes or no is having a Boolean value. Though you don't have to do this in JavaScript, it's good practice because you need to do it in other languages. So get in the good habit. That way, when you start doing other languages, you don't have bad habits. So while r dot length is less than target, we are going to be checking, see if I is prime. So what do we want to do here? Oh, you know what? Let's have this down here, because the first thing that we're going to need to do when we loop back around is reset it to true anyway. So if we just declare it right there, we can just keep it, in the lowest level scope it needs to be. So target, and then for let j equal 2. Again, we don't want to check to see if something is divisible by 1, because that's always going to be true, and that's not actually uncaught syntax error. Oh, it's telling me. Okay, well, k is less than I minus 1. Again, we don't want to check to see if a number is divisible by itself. That is useless information, and it would return back a false negative. So now that we've got it, we are going to say if I is divisible by j with the remainder of 0, right? This is the modulo. We talked about this in a previous video. Then we're going to set bool prime false. And then we also don't need to check any other numbers after that, so we can just break. So it's going to iterate through all. The only thing it's going to do is check to see if it's prime. Once it finds out that it's not prime, there's no need to stay in this for loop, so we're going to break. After we're done with that, our while loop ends right here. So if bool prime is still equal to true, then r dot push and then we need to iterate I. And got a return value set. So let's go ahead, clear this. Let's go ahead and try console.log prime finder. Just check to see. Same one we had in this example. Perfect. Now, unfortunately, this is not very streamlined. So if we try to find 1,000, oh, it still returns 1,000. Okay, let's try 10,000 and hope that it doesn't crash on me. So, oh, it did return. Okay, interesting. Well, there's still ways to cut down on this. So we are going to do that right now. So the first thing that we should check to see if we can streamline is this. Do we need to check all the numbers between 1 and or that are greater than 1 and less than the number that we're checking? The answer is no, we don't. What do we not need to check? Well, at the very least, we don't need to check any number that is greater than half of that number, because no number is divisible by a number that's greater than its own half. 24 is not divisible by anything greater than 12. 100 is not divisible by anything greater than 50. Second thing, we're checking even numbers, but we actually don't need to. We only need to check 2. And we know, I mean, 2 is automatically going to get kicked back, or kicked into it no matter what we do. This doesn't even go through, like, I guess it does enter the loop. No, it doesn't, because j is not less than 1, so it's not going to even enter into it. So, odd numbers, they're never divisible by a number greater than its own third. So we could even shorten this down. We would need to say equal to, but sorry. But that's something that we could do. Numbers are also, they never only are divisible by numbers greater than their own square root. So aside from 1, right? Like excluding 1 in itself, right? The set of prime factors of a number are never numbers that are just greater than its own square root. So even though 10 is divisible by 20, 50, 25, you need to have numbers less than its square root to compensate for that. So 25 and 4, 20 and 5, 50 and 2, right? So we only need to find out if one number can divide it. So we could actually say I, and we should get the same number. Oh, that's because the yeah, okay, there. A mistake on my part. So math.square root, that's how you find the square root of a number in JavaScript. We only need to check up to the square root of a number. We don't need to check anything back. So that's gone from checking the amount of numbers the amount of numbers that we're checking have gone from n to the square root of n. So that's the whole O value less, right? Yeah. So that's going to save a lot of computing time if we're checking for something that's higher than 10,000. We also, if we assume 2 is in it and we start at 3, instead of iterating by 1, we can iterate by 2s, and we're only checking the odd numbers at this point. So we've assumed that 2 is we've assumed that 2 is prime, and because of that, let's go ahead and do the same thing here. We don't need to check to see if an odd number is divisible by an even number. It never is. And try this again. Same answer. Getting it a lot quicker though now because it's checking a lot less numbers to get the same result. So this is about as streamlined as you get without introducing some higher level math. And I'm going to talk to you a little bit about that. So these are the 3 examples that I have. The first 2 are very much similar to what we've just done. The big thing that I've introduced here is instead of checking for or iterating through all the numbers, I'm actually saying let's only check the numbers that are we've already found out to be prime, because there's never a case where a number is divisible by only composite numbers. If something is divisible by 6, it is therefore divisible by 2 and 3, which are both prime. If something is divisible by 15, it is therefore divisible by 3 and 5, both prime. So we don't need to be checking for divisibility by prime numbers. We need to be checking for divisibility, or we don't need to be checking by divisibility for all numbers less than the square root. We only need to be checking for divisibility of prime numbers less than or equal to the square root. So we can see, let's just try console logging that again, making sure it is accurate. Again, same answer. So another thing that's going to save a bit of time. It's not reducing an n value by any means, but it, in the case of something like 101, instead of checking 10 numbers, you're checking 2, 3, 5, and 7. You're not even check. We don't even need to check 2, because we're only checking odd numbers here, and odd numbers are never divisible by 2. So 101, when we first set this up, was checking every number from 2 to 100 for divisibility. With 101 now, it's checking 3, 5, and 7. 3 numbers is a lot less than 100 numbers. It's got to do some extra math to get to that point, which means we're not actually saving as much time as we might otherwise. But that extra math is still going to be more than compensatory for higher level, or for higher numbers, right? When you're talking about checking for 104,729, right? We're not checking 104,728 numbers or 27 numbers. We're checking, we're checking less than 100 numbers at that point. So, well, yeah, we are. Because 100, well, we're checking exactly 100 numbers, I believe. Because there are, we're checking about 100 numbers. But yeah, so this is a really easy way to find prime numbers. It's very simple. You can change this around so that if you want to find, the first prime number that's greater than 5 million, you could say, while you need to declare, instead of an array, you'd want to declare, let prime equal, whatever. And then when you find a new prime number, set it equal to that. And while that is less than 5 million, keep on going. So we could, let's do return prime. Let prime equal to that array is making it easier for us to check previous targets. So maybe what we want to do is we would need to push into the array and then set the new target to you would say, as long as prime num equals 0, no, 2, while prime num is less than target, if it is true that it's prime, then prime num equals I. And then we return prime num. So let's say copy. Let's check 104, 125. So this is going to find the prime number that is just greater than this. Same number. Same number. So yeah, that's just a little bit of changing around, and we can set it up differently. There's one other kind of high level way of cutting down the amount of numbers that you're checking. It does require a bit of extra math, but all prime numbers excluding 2 and 3 fit the equation 6k plus or minus 1. So 5 and 7 both fit this equation. It's 6 times 1 plus 1 and minus 1, right? That's 7 and 5. 6 times 2 minus 1 plus 1, 11 and 13. It doesn't mean that every number that fits that equation is prime, but it means that all numbers which are prime except for 2 and 3 fit that equation. So because of that, all we need to do is check numbers that fit this. What this equation does is returns all the numbers that are not divisible by 3 or 2. So the first time it returns 5 and 7, and it returns 11 and 13, right? So what did we skip? Excluding, everything basically up to 5, we skipped 6, divisible by 2, and 3, not as important. We skipped 8, divisible by 2. We skipped 9, divisible by 3. We skipped 10, divisible by 2. We skipped 12, divisible by 2, divisible by 3. How is it doing that? Well, it's returning multiple. The first thing that it's doing is getting every multiple of 6, which is always going to be even. And what's next to even numbers? Odd numbers. And because it is multiplying by 6, that number is also divisible by 3. Well, if a number is divisible by 3 and you add 1 or subtract 1, it's no longer going to be divisible by 3. So it's returning odd numbers that are guaranteed not to be divisible by 3, and it's returning them in sets of 2. Well, every third number, or every third odd number, is divisible by 3. So that's how it's doing it. So you can set it up so that instead of starting at, we need to assume 2 and 3 are prime, and we're gonna go through 2 different loops where we're checking for each of them, and then we return. We actually want to return the target. What did I prime target? Just in case both of them return a value. I don't think I created a stop in this. Yeah, I didn't. It's going to give you the same answer. And in fact, yeah, I took out the console logs when I copied this in here. But you can see before I did that, it just kept on returning these numbers. Okay, I hope that that all makes sense. This is probably the easiest way for someone who doesn't, who's never worked with prime numbers to understand it. This adds another layer of complexity, so I wouldn't really focus on that. You can read up about that, though, and in fact, the documentation on Project Euler, once you saw it, gives you access to documentation, and it'll talk about this. But this is a really simple way. Um, it's it's one loop, or well, one loop inside another loop. But when you do this, you have to have one outside loop and then two inner loops, because you're checking for two numbers at any given point. So I hope this helps. I have all of this posted on my GitHub for anyone to take a look. But yeah,